In this video, I'm going to show you how to graph a rational function that contains a hole. It's one of my favorite topics in pre-calculus. A hole occurs in a rational function when there are factors that are common to the numerator and the denominator, and in the process of simplifying, a factor of the denominator is eliminated. Let's take a look at a specific example. Y equals x plus 4 times x plus 1 all over x minus 2 times x plus 1. And I want to highlight for you that there are factors that are common to the top and the bottom. X plus 1 occurs on both the top and the bottom. So what I'd like to do is I'd like to simplify this fraction and make it as simple as possible by eliminating those two factors. So I'm going to write this in a reduced form. Y equals x plus 4 over x minus 2. At this time I want to answer the Q list, which is that little list below the original problem. Now the Q list are like the puzzle pieces, and once all the puzzle pieces are in place, I can put them together to construct the graph that's going to occur over to the right. Now when I'm answering the Q list, I've got a choice. Do I want to look at the original function, or do I want to look at the reduced function? And I think most people would choose the reduced function. It's simpler, it's more simplistic and easier to work with. And that's exactly what we're going to do with one exception. And that one exception are the excluded points. The excluded points you must take from the original. So I'm going to go ahead and draw a box around that Q. It's going to be my reminder that I've got to take those from the original. I'm even going to draw an arrow connecting it to the original. And I'm going to answer that Q first, just getting it out of the way. So the excluded points are found by setting the denominator equal to 0. If I set the denominator of this original function equal to 0, I get 2 and negative 1. Now that that's out of the way, I'm going to answer all the other Q's from the reduced. The first Q that I'm going to answer is the y-intercept. The y-intercept is found by letting x equal 0. So I'm going to go ahead and do this on the upper left. So our y-intercept is 0, negative 2. Okay, now for the x-intercept. To find the x-intercept, we're supposed to set the numerator equal to 0. I'm going to go ahead and do that. So the x-intercept is negative 4, 0. Now, the x-intercept came from the numerator, which was x plus 4 to the power of 1. That means this particular x-intercept is going to be a pass-through. If this had been a power of 2, this would have been a bounce, and if this had been a power of 3 or any other odd number, it would have been a wiggle. But in this case, it's just 1, so it's going to be a pass-through. The next Q is for VAs. If you were to look at this reduced function, you might say to yourself, okay, I know where the VA is. There's a problem area at 2, and that's where the VA is going to be, x equals 2. So let's go ahead and write that. Now it's important that you write the VA as an equation. It's not just the number 2, it's a line, x equals 2. If we look where that line came from, it came from the bottom factor, which had a power of 1, which is odd. Odd powers mean VA will jump. So I'm going to put a little subscript j to remind me to jump. The rule of thumb is every excluded point plays a role, and every excluded point will either be a VA or a hole. Well, we already have the VA taken care of, and that's at x equals 2, but there is this value of negative 1 that has not been addressed yet, and that's where the hole is going to be. There is going to be a hole when x is equal to negative 1. So I'm going to set up an ordered pair, letting x equal negative 1, and then I've got to figure out what the y-coordinate that goes with it is. The question is, am I going to plug the negative 1 into the original, or am I going to plug the negative 1 into the reduced? Well, as a reminder, we can use the reduced for every single Q except for excluded points, and we've already done that. So really, that's the last time I have to look at the original function. So I'm going to take the negative 1 and plug it into the reduced, and I'll do that over here on the right. I end up with 3 over negative 3, which of course is negative 1. So there's going to be a hole at negative 1, negative 1. Now the next Q is to decide whether we have a horizontal asymptote, a slant asymptote, or polynomial end behavior. And to make this determination, you have to compare the degree of the numerator with the degree of the denominator in the reduced function. In this case, the degrees are the same, so we're going to have an HA, and the HA is going to be y equals the ratio of the leading coefficients. Well, there's a 1 in front on the bottom and a 1 in front on the, there's a 1 in front on the top, and there's a 1 in front on the bottom, so 1 over 1 is y equals 1. The last Q is for crossings, and to figure out if you have any crossings, you're supposed to set the reduced rational function equal to the value of the HA. So in this case, it's going to be x plus 4 over x minus 2 equal to 1 over 1. Cross multiplying, we get x plus 4 equals x minus 2. The x's drop out, and then we're left with 4 equals negative 2. But we know that 4 doesn't equal negative 2, so that's just nonsense. And this tells us that there are no crossings. Okay, all the Q's are done. The puzzle pieces are in place. Let's try to put the puzzle together. When I go to graph a rational function, the first thing I like to graph are the VAs and the HAs. It sort of gives me a structure to work around, a framework. So I'm going to start with the VA x equals 2. Okay, the next thing I'm going to put in is the HA, and the HA is at y equals 1. Okay, so I got those out of the way. The next would be the y-intercept, which is 0, negative 2. Got that out of the way. Let's do the x-intercept at negative 4, 0. Got that out of the way. So we've done the y-intercept. We've done the x-intercept. The excluded points have been addressed. One of them led to the VA, which we got. Now the next excluded point went for the whole, which is negative 1, negative 1. And you may wonder, how am I going to plot that? What does that mean exactly? Well, it's essentially going to be an open circle that the graph approaches, but it just goes right over top. And I'll show you how that's going to play out in a second. But for now, I'm just going to put an open circle at negative 1, negative 1. So that's done, and the HA has been accounted for. So all the puzzle pieces are now laying on the table. I just have to put them together. So I'm ready to graph this. Now when I ask my students, where do you want to start to graph, on the right or the left? Generally, they like to say where the points are. All the points are in the bottom left quadrant, and that's exactly where I'm going to start. And the overall shape, there's 3 choices. It's either going to look like a boomerang, a wiggle, or something like a parabola. In this case, it's going to look like a boomerang, and it's going to be captured by the borders that are above it and to the right. So it's going to look like a boomerang, and I'm going to show you exactly what this is going to look like. Okay, so there's the boomerang on the lower left, and we said that this VA here is going to jump, which means I'm going to jump up to the other end, and I'm going to do another boomerang that's going to come down and to the right. So here's my rational function that has a hull, but there's one last thing, and it's very important, and your teacher is going to be so happy that you did this if you decide to do it, and that's to label. It's just going to make it much easier to see this. This is our HA at y equals 1. This is our VA at x equals 2. This is our x-intercept at negative 4. This is our y-intercept at negative 2. And now I'm going to try to fit this in here. This is going to be the whole at negative 1, negative 1. And this right here is an awesome graph. A+, get excited to do this on your next quiz.